In this video, I'm going to talk to you about kinetic molecular theory and Graham's law. Now, by definition, the word kinetic means of or relating to motion. So, kinetic molecular theory, or KMT, explains the behavior of a hypothetical ideal gas, and it is very useful when analyzing and looking at behaviors of gases. KMT makes a number of assumptions to explain the reasons why gases act the way they do. I'm going to go over the 5 assumptions of KMT. First, KMT is assuming that gases are tiny molecules, which they are, but they are in random straight line motion. Gas particles are point masses with no volume relative to the spaces between them. In other words, the volume of gas particles is so small with respect to the spaces between them that we can consider that volume negligible. Number 3, there are no attraction or repulsion between particles. In other words, there are no intermolecular forces that exist between these gas particles. The average kinetic energy of a gas particle is directly proportional to the temperature. Okay, so kinetic energy mathematically is defined as 1/2 multiplied by the mass of the object multiplied by the velocity of that object squared. Recall that when we're referring to and talking about gases, we're going to use a temperature scale called Kelvin. Kelvin is an absolute temperature scale in which we will add the degrees Celsius to the number 273 to get Celsius converted into Kelvin. Gas pressure is due to the molecules and the number of collisions that are occurring between the walls of the container or the vessel. And we explored that in a PHET simulation in gases video number 1. At any given temperature, the molecules in all gases have the same average, please underline average, kinetic energy. This energy is directly proportional to the Kelvin temperature. In other words, as temperature goes up, kinetic energy goes up. As temperature goes down, kinetic energy goes down. That's what we mean by directly proportional. So let's look at this graph, which shows a number of gaseous molecules as a function of their kinetic energy at 3 different temperatures. Let's start with 300 Kelvin. And again, to give you an idea, room temperature is 25 degrees Celsius. So 25 degrees Celsius plus 273 Kelvin tells us that this is 298 Kelvin, to give you a bit of an idea of what temperature we're talking about here at 300 Kelvin. As you can see, there are a number of molecules here, and most molecules have a relatively low kinetic energy when compared to 400 and 500 Kelvin. As temperature increases, we see a shift where now more molecules have a higher kinetic energy, and that is showing this directly proportional relationship. However, the number of molecules here is not changing. We're just seeing an overall shift to a higher kinetic energy as temperature increases. Graham's law of diffusion and diffusion, which I'll define in a moment, shows that the rate of diffusion is inversely proportional to the square root of the molar mass. So mathematically, this would be expressed as you see right here. So the rate of diffusion is proportional to 1 over the square root of the molar mass in grams per mole. we would describe this mathematically as the rate of diffusion is inversely proportional to the square root of the molar mass. In other words, lightweight gases are going to diffuse at a much higher rate than a heavier gas. If you consider our formula for kinetic energy, 1/2 mv squared, well, mass is the amount of matter. Okay, so we're not going to see that changing. It's going to be constant. However, the velocity is going to change. And we learned in this kinetic molecular theory and in gases 1, as temperature goes up, so does the motion. The velocity increases. And so this leads to a number of gas laws that I'm going to be going over in upcoming videos. Let's take a look at this animation here. This is showing diffusion, which is the movement of these gaseous molecules from high to low. And we see them mixing, actually forming a solution of gases. And we're showing that as they diffuse, these smaller lightweight ones move faster, and overall we see that this mixture begins to move a little bit faster, but there's more molecules now. So this is going back to what I just talked about. We've increased the overall number of molecules, so you see the overall speed increasing slightly, which is driving up and increasing the average kinetic energy. Now let's compare that to effusion. Effusion is the process where gas molecules escape from a previously evacuated vessel or container through a small hole or a small pore. And in the animation on the right, you can see when the hole is open, the molecules escape through that small hole. But what do you notice is the smaller molecules, which are moving faster, are able to effuse and escape from the vessel here much faster. So that is effusion as compared to diffusion on the left. All right, so I'm going to define Graham's law. Now, Graham's law was formulated by a Scottish physicist named Thomas Graham. And it states that the rate of gas molecule 1 divided by the rate of gas molecule 2 is equal to the square root of the molar mass of molecule 2 divided by the square root of the molar mass of molecule 1. Now, rate is an expression over anything over time. So meters per second is a rate. Miles per hour is a rate. Molar per second, which we talk about in kinetics, is a rate. So I'm going to go ahead and derive Graham's law. Now, this is predicated on the fact that the average kinetic energies for these gaseous molecules will be the same. So this derivation will start with 1/2 m1 v1 squared. And we're going to set that equal to 1/2 m2 v2 squared. Now, m is the mass, or the molar mass. V is the velocity, which is a rate. So we're talking about the rate at which molecules will diffuse or effuse. Rates could be as high as thousands of meters per second for a gaseous particle. All right, now I'm going to multiply both sides by 2 or divide both sides by 1/2. That's going to get rid of the 1/2. All right, so if you multiply this whole expression by 2, you end up with the following. Okay. Now, I'm going to start isolating some variables here by, I'm going to multiply both, or excuse me, divide both sides by m1. That means this goes away. I'm going to divide both sides by velocity 2. Okay, so velocity 2 squared. So this goes away, and all of a sudden I have velocity 2 squared over on this side. Now, I'm going to take the square root of everything. Okay, so the square root of this entire expression will give me velocity 1, velocity 2 is equal to the square root of mass 2 over the square root of mass 1. Okay, mass being the molar mass, velocity being the rate. So it's very important to me, anytime you have a new expression or equation, that you understand where it comes from. So we're going to do lots of derivations next year in AP Physics, but this comes from the fact that the kinetic energies are the same, so we can set them equal to derive Graham's law. So this allows us to compare the rates that particles, gaseous particles, will effuse or diffuse under the same conditions. In other words, constant temperature, pressure, and equimolar. So the same number of moles. All right, so like we talked about in the graph, we're going to keep the number of particles constant, pressure constant, temperature constant. Then we can find and compare the rates under those conditions. All right, so what I want to do here is one practice problem. Carbon monoxide effuses at a rate that is 2.165 times faster than that of an unknown noble gas. Calculate the molar mass of the unknown gas and determine its identity. Now, I find students struggle with Graham's law computation, so I'm gonna try to give you some bits of information to make this a little easier. First, when solving Graham's law problems, identify which gas is lighter and call that gas 1. So rate 1, molar mass 1 for the lighter gas. What this does is this gives you a rate ratio, which is referring to this right here, that is greater than 1. It's just easier to work with it that way. You can solve it either way, but this makes life a little bit easier. So let's look at what we know. So we know rate 1, which is carbon monoxide, is 2.165. We don't know rate 2, okay? But we do know some information that will allow us to infer facts about rate 2. So let's look at the molar masses. So we are asked to find the molar mass of our unknown gas. And we know the molar mass from the periodic table of carbon monoxide. Now here's the key. You're told it's 2.165 times faster. So one way to conceptualize this is for every one molecule, one particle of the unknown gas that effuses, 2.165 get through. Okay, so the lighter one is 2.165 times faster. Again, for every one of the heavier unknown gaseous particles that effuses, over 2 of the carbon monoxide effuse. That's a really good way to think of this, okay? That allows us to do this. We can say, all right, rate 2 equals 1. 2.16 divided by 1, that's 2.16. Now we can set that equal to our square root of molar masses, gas 2 and 1 respectively. By doing that, we can say that by algebraically multiplying both sides by the square root of the molar mass of carbon monoxide, in other words, 28.01 grams per mole, we can isolate our unknown variable and solve. Therefore, we can find that our unknown gas is indeed xenon. All right, so algebraically here, We're squaring both sides to get X. X is equal to 131.3 grams per mole. Looking on the periodic table, you can find the identity of this unknown gas. So in this video, we've continued to look at our Georgia Standards of Excellence that are dealing with the relationship of gaseous particles, pressure, volume, temperature, and of course, the number of moles of those gaseous particles. I'll see you guys in class.